So as we've outlined in lecture or in the lecture section of the videos, we're going to build a spreadsheet to do the analysis of the deflection of our mullion or a facade element. And I'm just going to remind you again, this idea of looking at that wind load across that panel system and being simply supported at the top and bottom by the floor. And then this formula, P is equal to pressure is equal to this coefficient times the velocity squared. And in this case, the velocity squared is in miles per hour. And there's a little bit of a kind of check back to this formula. If you look at the design loads according to code, we have this idea of 20 pounds plus or minus per square foot. Maybe on the corners up to 30 square feet as minimum design loads. And when we get to the calculations, you'll see that there is some alignment with that. So as a matter of fact, I can show you just at the bottom corner of this one behind my head, we have a wind speed that develops that kind of 23 to 30 mile an hour, or excuse me, 30 pounds per square foot load. And that's in the category 2 or category 3 storm rating. And that I've outlined as being in the code area where the governing bodies say we need to design for wind loads in excess of 111 miles an hour. So anyway, that's the, let's now take a look at that spreadsheet and how we'd actually do those kind of, generate those kind of calculations. So I'm going to pull up the actual Google Docs spreadsheet that I created. If you don't use Google Docs, you could use Excel. It's just as acceptable. And we're going to look specifically now, we're going to, next, after we cover the wind, we're going to look at the actual deflection calculations. But I'm going to slide the spreadsheet over until we come to this area of wind loading. And I want to explain a little bit about what I've created here and kind of what our learning goals are. So I've done a snippet. I Googled wind speeds and categories of storms. So we have 4 from 1 to 5. And this gives us the speeds of the wind and all kinds of value systems, but we're using miles per hour. And then I've gone down here and used that concept to generate this chart. So I labeled an axis wind miles per hour, and then I just created data. So it's 10, 20, all the way up to where we get here, it turns to 96, because that is the definition for a category 2 wind. As you'll see up on the top here, that's defined as 96 miles an hour to 110 miles an hour. And then I jump to category 3, which is 111. So I don't go to 80 to 90, I go to 96, then I go to 100, then I go to 111, which is the actual break point for category 3. And then I keep incrementing up at 10 until we get to the break point of, I said 130 for category 4. And let's see what that says. That's 130. And then 157 is actually the break point for category 5. And you'll notice no matter how much higher wind speeds go, we have no system for designating storms above category 5. And we're talking about an immense amount of destructive power at that level. So I made a chart of numbers, a list of numbers. And then along here, I created a formula. So that is that power, that velocity squared, so it's a power function. So I take the number that I've generated in this column and multiply it by the coefficient. So it is that coefficient from the chart I showed you, 0.00256, and that gives us a 0.26 pounds per square foot. And then I just took that function, and you can copy it, and then if you string down over the next set, you can go paste, and it will just paste accordingly. So each one will increment up to the next step. So now it's L33 times that squared times that coefficient. So it'll automatically take care of incrementing us up. Now the way we're going to end up generating a chart from this is really quite simple. If you're using Google Docs, you just select the blocks that you want to label. And I think even if you carry the names in, it'll automatically add those as labels. It didn't in this case, but it might if you do a certain setting. But here's your chart generated for you. And then you can go in and customize it by changing the labels on the axis and give it a name. So you'll see this is a little larger chart, but if I actually wanted to, I could compress this down so it fit on a smaller form factor, so to speak. Now, so do that, and you'll see, you'll notice what I've done. I've labeled the wind loading and the wind speed. I don't have this axis labeled. I should go back and correct that. But I'd like to see something like that on your chart just to show this analysis. And I want to point this out because I hope you can see the logarithmic function here, this squaring function. This is, if you look at this curve, it's a parabolic shape. So it starts out with a relatively low angle of attack and gets increasingly sharper as it starts to head up here. So this is 1/2 of a parabola, if you can remember back from trig, because we have a squared function and that kind of defines that shape of a parabola. And I made another chart over here, and I want to use this just to kind of demonstrate this power of the wind speed to kind of wreak havoc with our architecture. So I made a chart which is the identical chart, the wind speeds times the actual winds to get per pounds foot. And then I made a chart that doesn't have a squared function in it. So now I'm just taking the wind speed and multiplying it by 0.1. I'm using 0.1 because that kind of brings us into alignment with these initial starting numbers. If I multiply the wind speed times 0.1, I get 1, 2, 3, 4, 5, 6, so to speak. And you'll notice how they track very closely with these actual numbers here at the bottom. And so I'm going to grab all of these now, and I'm going to click chart. And this is the significant chart that we get. If you'll notice now, this is that same blue line that I've talked about. That's the blue line that matches the chart down here. If I was to shrink this chart down a little bit, you'd see how that has the blue line has a parabolic shape to it. But you'll notice the red line that isn't a square to the velocity of the wind. And that's what we would normally think about this idea of the wind speed increasing in a linear function as far as pressure on a system. But in fact, it isn't linear. It continues to go up like this in a very extreme way. So these high speeds contain a lot of, if you think about the idea of the force that's available, you think about this area under the parabola. If you, in calculus, we learned that we can calculate the area under a curve. And in this case, notice the difference between what we would think if it was just linear increases in wind speed and if it was a squared function, how much more force is available to deflect our structure. So that's really why I want you to go through this kind of exercise, at least to start to gain the first idea about wind loading. But there's something else here. It just gives you a chance to experiment with using spreadsheets. I think it's really important for all kinds of people in technical fields to have good command of spreadsheets, to do analysis, to create communication documents. And these tools are really very accessible and very easy to use and really powerful, like this idea of quickly creating graphs from data that you construct. So that's the section on the wind speed. This is kind of what I would expect, a hand-in chart to have, some kind of a capture of what category wind speeds are, a chart that you made, or excuse me, a table that you made, and then a chart that goes along with it. And then next we'll look at the idea of deflections and the effects of wind loading on the deflection of our design wall system that we're going to create.